you can go a bit slow. You have more time. Go slow.
Good afternoon, everyone. My name is Hong Min Hong. This is my paper title, Manufacturing Manager for Decoder Picture Bar based on Scalable High Efficiency Video Coding. This is my outline. First, introduction. Second, overview of SHVC. Third, proposed VDPBN method for SHVC. Fourth, simulation result. Final conclusion. First, introduction. With the rapid development of electronic technology, the ultra-high definition resolution of 4K by 2K or 8K by 4K will become the main video application in future. Therefore, the JCTVC has been developed a new high-efficiency video coding to satisfy the UHD requirement in 2010. And the first version of HEVC was approved as ITUT H.265 in January 2013. ISO code and paper H, ITUT code H.265, and the JCTVC code HEVC. To upgrade the HEVC used in heterogeneous access networks, the JCTVC has been approved scalable intention of HEVC, called SHVC, in July 2014. The function of SHVC includes spatial scalability, temporal scalability, and external scalability. Second, overview of SHVC. Based on the HEVC, the system of SHVC code includes base layer called BL and the enhancement layer called EL. The SHVC supports multi-looper solutions by enabling different inter-layer predictor. In multi-looper architecture, a full decoding loop takes place in every intermediate layer need to decode a target layer. The multi-looper decoding architecture called NLDA can achieve higher coding efficiency than the single looper decoding architecture called SLDA. But NLDA increases the decoder picture buffer size and the memory bandwidth for motion compensation on the decoder side. This leads to the reduction of decoder performance for SHVC. Two important parameters to set the DPP size according to specification of HDVC are listed as follows. First, resolution of decoder frame to decide the max DPP size. Table 1 specifies the limiter for each level from the spec of HEVC. We choose the base keyword sequence with a resolution of 832 by 480 to illustrate the impact of DPP size. Firstly, we find the parameter of maximum picture size of DPP equals to 2,228,224 bytes from table 1 and selecting level 4 to decode. In addition, the value of picture size in sample 1 should be less than or equal to the max DPP size, which is derived as follows: ISO spec of HEVC, where maximum PS is specified in table 1 and the max DPP picture buffer is equal to 6. Finally, we can calculate the required max DPP size equal to 16 frames from ISO spec of HEVC. Second, number of reference frames to design the required DPP size. To describe an impact of number of reference frames, we take a random access called RA profile. The size of the group of features called GOP equals to A, and the active frame equals to 1, as the decoding conditions to illustrate. So we can obtain the max number of reference features, called max reference feature number, equals to 4 from the decoding regularity of reference feature and the feature order counter. Finally, we can set a DPP size equals to 6. Therefore, DPP will occupy huge memory by decoding video sequences of 8K by 4K in BL and 4K by 2K in EL for spatial scalability of SHVC. So, to reduce the DPP size of SHVC, recently, Sud et al. Proposed a dynamic virtual DPP called DVDPP assign algorithm, which exploits interlayer correlation between BL and EL to predict the decoder feature to several DPP size. They divide the DVDPP into two parts, including a fixed DPP size, setting a half of original DPP size, and a virtual buffer called VB to reduce DPP size. However, the DVDPP method is ineffective for video sequence with compressed content and active motion, and the memory saving ratio called NSR means a bottleneck when using the sum of absolute difference called SAD as a simple measurement. So, we propose VDPBM method for SHVC. We take an observation from the prediction structure of RA for SHVC. We can classify the decoding frame order into 4 labels when GOP equals to A. From the prediction structure of RA, we can find the label 1 and label 2 are the major and unavoidable reverse frame. The decoding frame in level 3 and level 4 can be fully predicted from the frame in the level 1 and level 2. In the same situation, we also can find the decoding regularity of reference frame meet our observation frame GOP equals to 60. And so on. The decoding regularity of label N equals log 2 GOP. Therefore, to follow several DPP size of SHVC, we design a virtual DPP manager called VDPVM to control and store the parameter and the decoding data. Firstly, the VDPVM is divide DPP into two types of static DPP called SDPP and the dynamic DPP called DPP. From the observation, the VDPVM can set SDPP size according to GOP and the max reference feature number as follows. The VDPVM decides DPP size by analyzing SAD between the current decoder frame and the reference frame. For fast and accurate finding the predicted CTU, we adopt well-known three-stage search algorithm called TICEAS to reach the target. A threshold of SAD is set to check whether it is good enough for reference frame in the VDPVM. If E is less than the threshold, only record index parameter of the current decoding CTU in DPP. The proposed DPP size and the cell appears NRY are defined as follows. Figure 2 shows the relations of cells pierce NR1 vs DPP size, which indicate that the cell pierce NR1 is approximately the same for all thresholds. So we chose the threshold equals to 2,500. For simulation result, for evaluate the memory segment efficiency of the proposed VD-PBN and the DV-DPP, we compare the coding efficiency with the test reference software SHN 4.0. And the simulation condition as follows. And the test sequence as follows. The ASR is defined as follows. For QP equals to 32, the proposed VD-PBN method further achieve an average NSR equals 33.72% to compare with the HN 4.0. And the sequence of compressed content and the active motion are improved significantly. Figure 3 shows the performance comparison of the proposed VD-PBN and the DV-DPP with different quantization parameters, and the experimental results show that the proposed method can achieve an average NSR about 33.36%. Final conclusions. Compared with the DV-DPP algorithm, the VD-PBN can further achieve an average NSR about 7.7%. And it is clear that the proposed VD-PBN can efficiently reduce the DPP size of SHBC. Thank you for your attention.
Any questions?
May I ask a question about, do you consider the computation complexity when using your system, your proposed system, your method to set DPP memory size? I mean, how long time do you run the VD-PBN? Why, if you after the SHVC real-time encoding? How do you think?
Please, pardon.
Okay. My question is, it implement when you run your VD-PBN method to set the memory size, to reduce the memory size. Does it real or ever the SHVC real-time encoding? What's your opinion? Yeah. If you would ever your SHVC real-time encoding?
Real-time encoding.
If implement your VD-PBN method, if you will ever your real-time encoding, or doesn't matter. If it doesn't matter, or ever your DV time, your SHVC time encoding. Yeah.
Time.
The time. Will be ever. Yeah.
Do you mean the encoding sequence?
Yeah. I mean, when you use your VD-PBN method, does it ever or it have any relationship when you when your SHVC do real-time encoding? Does it ever? It have any relationship with, or any, does it will make your SHVC real-time encoding whatever or discounting or describe? Yeah. I mean, yeah. Do you know what I mean? Yeah. Okay.
See, the DPP size you have reduced. Space is reduced, so time will increase. There is this space-time trade-off.
DPP size.
So the question is, you'll take additional time to reduce this space.
Yes.
So how much? What is the trade-off? How it will become slower. If we had all the TPP we wanted, then we wouldn't have to do these calculations for threshold, etc.
Yeah. I mean, how many seconds? How many seconds does it ever your SHVC real-time encoding. Yeah. How many seconds does it?
It's faster and
Time. Yeah.
Right.
How many times will it effort will effort HSVC real-time coding? Yeah. How many seconds does it need to run?
That you not reported actually.
Okay. I mean, just mention my you have the data. Okay, but I just want to you consider this kind of a situation will happen. Yeah. Do you consider it
yes,
before?
yes.
You
I consider.
yeah. So you had to consider this kind of situation will happen, right?
Yes.
Okay. What in your articles? Okay. Thank you.
In that last figure, where you have this graph, this one. On the x-axis, you have this QP. So QP, higher QP means lower quality or higher quality? QP is what? Quantization, right?
Yes. On the session
So
server.
if we go higher QP,
Yes.
it is better, higher quality or lower quality?
Higher quality.
Higher quality. So MSR is reduced, and your it is more flat. It is not depending on QP very much. That is an advantage. Okay, thank you.